So we're now on to a subject very close to my heart. This has been somewhat of a personal crusade over the last few years, where we've seen a steady decrease in temperatures of heat networks, of domestic hot water over time. In particular, spent a lot of time speaking to NHBC, who initially had 60-degree requirements, dropped to 55. I'm very happy to announce that we've now got the industry in a place where we have got cohesion, or everyone to agree on a particular approach with HIUs with instantaneous domestic hot water generation. So only responding to that. Want to invite Andrew Mackay, who's the has actually been chairing the CIBSE Domestic Hot Water Working Group, which I also sit on, which Phil Jones mentioned earlier today. He's on as well. Welcome, Andrew.
Hi, good afternoon, everyone. Very pleased to be here, and thanks very much, Gareth, for the introduction. Gareth, I'm not sure I've got control of your screen.
That's fine. If you just tell me, I'll flip through. Yeah.
Brilliant. Thank you very much. So yeah, that's a nice little introduction. So I'll launch straight into it, I think. So if you flick to the next slide, please, Gareth. I'm going to talk a little bit about the requirements for domestic hot water, but I think this slide kind of shows the big one for me, really, which is one of the main reasons why we're doing it, which is the climate emergency and how that's affecting everything that we previously thought we knew about our industry and how we design. So if you flip to the next slide, please, Gareth. I feel like probably I'm preaching to the choir a little bit here, but these are a few diagrams that show the importance of what we're trying to do, particularly in the communal heat domestic business. So we have our target of trying to hit 20 net zero by 2050 as in the UK, and as you can see from that top left diagram, that's showing all of the energy that's used in the UK in 2018, and around about 35% of that is domestic, so energy that's used in the home. And one of the huge challenges associated with that is that big block, which you might not be able to see if your resolution isn't big enough, but the biggest block in that domestic is 70% of that is currently natural gas. Obviously, that's a huge blocker in terms of what we're trying to do and moving the UK towards that net zero position in 2050. The good news is we've done a lot of work over the last 15 years as an industry, and you can see in that top right diagram, this is an actual specific project example of a development that Arup looked at, where we were looking at interventions. And on the left-hand side, you see the chart of how we were expecting that development to use energy at its current status, and by bringing that up to modern standards of insulation and air tightness, we move right the way across that right-hand block where we are at 25% of the total energy. But what you can see is that moves from being a space heating problem to very much a hot water problem. If you could go to the next slide, please, Gareth. And at the same time this is all happening, we're also we've moved a huge way in terms of our culture and the way we use hot water. So slightly tongue-in-cheek picture off on the left-hand side, but that's where we were in London 150 years ago, where we either didn't wash at all, or we had communal baths, and very few people had that access to hot water. And we moved through a series of kind of technical innovations, moving to having individual heat generation within our own homes, whether that's back boilers on burning stoves or coal, or whether that's moving forward to gas boilers from the kind of the 50s onwards. But that was all based around hot water storage, because we used to use a lot of hot water and use it quickly from things like laundry and baths. Whereas now we're moving across to this, what I might call the Scandinavian approach, where we might not all have saunas in our homes just yet, but we're predominantly a showering culture. We don't use very much stored hot water for laundry anymore, and we're moving towards a world where we're connecting as many low and zero carbon sources to heat networks to generate heat for our space heating and hot water from a low carbon perspective as much as possible. So next slide, please, Gareth. So to go back to the reason why hot water is really important is that it's not only the majority of the load, but also it's driving the temperature of the heat network. We can use space heating down at 35 degrees if we wanted to, and we'd have some big emitters, but that would be okay. We could get that to work. But actually, we know that we need hot water to be a certain temperature, whether that's for function or for safety. So that brings the temperature of the network right up, which drives the heat losses and drives the technology that we use. We've talked a little bit about heat losses already, but you can see on that diagram that you'd already seen on the Arup project, and actually that heat loss becomes even more significant when we're down at a low heat demand network. And so this is a start for that table there, which gives you a bit of a start into why we think this is really important. So just by dropping the temperature from hot water in a flat at 55 degrees down to 50 degrees, brings our network temperature down by 5 degrees as well, and gives us straight away an 11% reduction in heat losses through that network, which is a huge benefit. So you can move on one more slide, please. And it doesn't stop there. So I mentioned earlier that the hot water temperature actually affects the technology that we can use. And in a net zero economy, we need to be generating heating from electricity, not from gas anymore. So we need to be looking at heat pumps. And heat pumps, the bigger the temperature difference between the water that we put in and the water that we take out, the harder the compressor in that heat pump has to work. So more electrical energy in means more energy consumption. So the lower we can bring that temperature down, the less hard the heat pump has to work. But actually, there's another technical barrier, which is the availability of refrigerants. So refrigerants have their own global warming potential when they're accidentally released. They have flammability concerns, and all of these things mean that there are very few refrigerants that are available to use safely, particularly after 2025, and they also limit the high temperature that we can achieve from heat pumps. You can see on the right hand side that diagram showing that just by dropping that temperature by 65 degrees to 60 in terms of the heat network, so similarly a 5 degree drop from 55 to 50 inside a flat, you can get as much as a 20% reduction in energy consumption by those heat pumps, which is again huge. So if you move on one more slide. And let's not forget about this one. It might be something that is just an annoyance to us, but Limescale actually also, other than reducing the lifetime of equipment, it also has an impact on the energy consumption as well. And you can see here that just the 10-degree difference between 50-degree water and 60-degree water gives you a 20% increase in the Limescale deposition. So the lifetime of your HRU goes down, your TMVs inside apartments, your other plate heat exchangers that you've got elsewhere in the heat network require more maintenance. All of that adds up, but at the same time, you also get a reduction in performance across plate heat exchangers and also on your heat generating equipment, whether that's a heat pump or something else. So we skip on. But we know that hot water temperature is also very important for the safety of the users. That's for two reasons. One of which is scalding. So the table on the right hand side, I think, is very interesting and talks about the different amount of time that it takes for you to get a severe burn with the exposure to different temperatures. And the column that interests me most is 50 degrees and 55 degrees, and particularly that bottom row where it's the difference between a child receiving a second-degree burn is 45 seconds at 50 degrees and just 3 seconds at 55. So that's really the difference between a child screaming out and getting some help if they're immersed in hot water, and an adult coming from the next room, or a child experiencing some significant trauma. But Legionella is also very important and is an ongoing issue in the UK. So we've done a lot of work with HSE as part of the CIBSE Hot Water Working Group. And we've been through guidance, and we're very happy that HSE's guidance on preventing Legionella allows us to use a 50-degree hot water temperature in the environment that we're talking about, which is very specifically HIUs generating hot water instantaneously in a typical domestic setting. So the reason that 50 degree is acceptable is really to do with the low storage that's in that system. So there isn't enough hot water to generate a viable population of Legionella bacteria. And so 50 degrees is ample temperature for us to use that hot water safely, and also potentially improve safety. Can you move on one more slide, please? But what about what we actually use the hot water for? So these are the two main reasons I think that we worry about hot water temperature. Is it going to take ages to fill my bath? Actually, it will take longer than if you have a hot water storage tank. But what we're not talking about here is a comparison with a hot water storage tank. We're talking about a comparison in a new build to other types of technology that would be used. And when we're talking about new builds, we're talking about a flat that's got a TMV that's limiting that temperature for safety reasons to 48 degrees. So really the difference between 55 and 50 makes absolutely no difference to the ability of you to fill up your hot water, your bath quickly. And is 50 degrees hot enough to do your washing up with? Is it hot enough to remove grease? And I know that Gareth can talk at length about this, and probably be very happy to later. But yes, the answer is, and it's above and beyond the temperatures that the soap manufacturers expect their products to be used at. So 55 degrees is too hot, you can't really put your hands in it. 50 degrees is definitely hot enough. And actually, when we compare that to what people are doing when they've got free choice out in the field, Energy Saving Trust did a study of combi boilers across the UK and looked at what temperature they were set at. And actually, the majority of them, more than 50% of the boilers, were set to deliver hot water at less than 50 degrees. So as a country, we were already more or less happy with it. Next slide, please, Gareth. So what have we been doing in terms of the hot water group is we've been aligning our reviewing all of the standards available, reviewing the technical requirements and the safety requirements, and trying to align that, and as Gareth touched on earlier, trying to consolidate it and influencing the industry to somewhere where we think is best practice for safety and best practice for our future ability to mitigate the climate emergency. Thanks, Gareth.
Great. And I'll just add to that. So under CP1 2020, and this is actually also coming out from the CIBSE Domestic Hot Water Group, there is a requirement to generate hot water at 50 degrees, that you are able to generate 50 degrees. Based on conversations with HSE, it's really important to emphasize this is for the specific use case, but what we're talking about here is effectively they're similar to point of use devices, and they're considered to be a low risk of Legionella from that perspective, so low risk systems. And when you're looking at balancing, 50 degrees is sufficient as a generation. This just comes back to one of the points that was asked in an earlier session around 50 degrees within 60 seconds at the tap actually isn't a requirement. It's a requirement that you generate at 50 degrees from the HIU. And that's one thing to be really clear on. One of the things that came out of that was, well, okay, at that point, there isn't a time requirement on temperature that has to be delivered to the endpoint. And it's felt that it's actually really important to come in with on that to have something around the customer comfort perspective. So we now have under CP1 2020 a requirement of delivery of 45 degrees domestic hot water to be achieved within 45 seconds. That's minimum requirement 3.4.17. And the rationale for this is, as Andrew showed in his slide earlier in that table, actually 45 degrees is functionally hot is the point at which scalding can occur, and it will take a long time, but it is actually painful to touch. So from a functional perspective, that's actually hot, and that's a sensation that a customer will be getting. Coming back to the traditional approach, it's more of a equivalence to 50 degrees in 60 seconds, and there's anecdotal evidence suggests that this is the flex point for complaints. Conscious on time. So we're balancing off that 45 degrees within 45 seconds. We've got a requirement at the same point in time for reduced flow rates to be used in building regulations. In particular, if you look at Part G, there are optional requirements under Part G. We tend to see those being used in localities where heat networks are more prevalent. And if you just apply this, there's a standard table that you can apply to use those. You see that kitchen sink taps, for example, tend to be around 6 litres per minute as a maximum. You can obviously do your own calculations to go above that if you make flex to other areas, but what we're seeing is that actually quite often in practice, trade-offs and flow rates being used where actually people are going below the 6 litres per minute because they're trying to get a higher shower, for example. We've been doing acceptance testing, so we pioneered acceptance testing. It's great to see that that's now in CP1 2020. We've been doing it for 5 years. We've actually been doing the testing of 45 degrees within 45 seconds for 5 years now. And we've actually found that the failure to meet that 45-second target is the single largest problem that we've identified. Issues around that are pipes are generally oversized, so don't account for lower flow rates, so people haven't made that change in design. And also we've seen that plumbing outlets are often plumbed in series, so you go through to a bathroom at a large diameter and then go off, for example, to kitchen sink from there, which adds a significant volume of water that needs to be cleared at each each draw off. I'm not going to go into here. Alternative approaches have got inherent issues on heat networks. I won't go into that. Recirculation really wouldn't be advised. And trace heating in practice, we've seen a number of issues around Legionella, somewhat ironically, where poor installations leading to higher temperatures being maintained in pipe work. And it also leads to overall higher energy use. So what we need to do is move away from that and actually look at how we're designing tertiary domestic hot water pipe work. And we're suggesting we take a different approach. First thing, we need to reduce pipe work sizes. So size pipe work based on flow rates and distance and push to higher velocities. And then we'd also really strongly recommend moving to a domestic hot water manifold approach where you're minimizing the volume pre-manifold and then running a single pipe to each outlet and sizing that pipe to the flow rates that you need for that outlet. Manifold approach, what we look, again, I mentioned it before, so we try minimizing, so less than 0.5 meter between the HIU and the hot water manifold to minimize the volume of large bore pipe work that you have to draw down each time to clear, and then individual pipe runs. If we look at what's influencing the factors on domestic hot water delivery times, really 3 issues. One is the HIU warm-up period, time to generate hot water from the HIU. The BESA HIU tests will actually show how long that takes. There's then time to clear the pipe work of the cold water. So you look at the volume of water, so pipe length and diameter versus flow rate. And those are the 2 things that we normally see being calculated. There's actually a third element, which is the warm-up time for the pipework itself. So there's a cool-down effect due to thermal mass of the pipe wall. And that's not normally factored into calculations, but can actually have a really big impact. And it's quite difficult theoretically to calculate as well. We carried out in situ testing to explore the impact of domestic hot water delivery times. So we got a whole series of different pipe diameters. We used 2 different manifold systems. We varied flow rate and then pipe size and pipe length. And we recorded temperature readings every 5 seconds until we got a stable temperature. And we looked at flow rate, and then we recorded a bunch of data for each test. We use a standard setup. So there we've got pipe, we've got a manifold, and then we controlled flow rate at the outlet and measured temperatures. I think, again, I'm being signaled on time. So I'll try jumping on. What we found is that short runs introduce minimum cool down effects. This is internal diameter 14.2 millimeters at 6 liters per minute. And what you see is you get to 45 degrees in about 14 seconds from that. So this is only 5 meters. So you've got down bottom time to clear the pipework cold volume there. You're talking about 8 seconds. Then you've got your HRU warm up time, about 6 seconds. So you're then delivering. If you then look at the same setup for 25 meters, you've got the same time. So again, you've got the same HRU warm-up time to clear pipework of cold volumes a lot longer. But the thing that a lot of people, again, not take into consideration is this big cool down effect of the pipe work, which has really increases delivery time. It's quite difficult to capture theoretically. So in this instance, 14.2 mil, which is similar to 15 mil, where you'd see with copper, you're talking about 45 degrees in 90 seconds. So double the time that you actually is requirement under CIBSE, under the CP1 2020. So I guess coming through highlights, what we've got here is looking on the left, we've got temperature on the vertical axis, and we've got time in seconds. And then it's showing with, again, this internal diameter of 14.2 mil. What we're finding there is, okay, at 5 meters, it's fine, but as soon as you start getting to 15 meters, 25 meters, you're not hitting timeframes, and this is what we're seeing. Whereas if you're to step to smaller diameter, so on the right, we've got internal diameter of 8.8 mil, you are actually managing to hit 45 degrees, even when you're going out to 25 meters. And interestingly, when we brought lots of people to site to actually come and listen to it, there's no audible difference in pipe noise and noise between these two different tests. So that's really quite important. Also want to note that even at 9 liters per minute on longer pipe runs, actually larger diameters can still be a problem. And again, you see you're meeting it, just getting there on 15 meters, but at 25 meters, again, you're getting that problem. Even at 9 liters per minute, your 45 seconds you're not meeting. Whereas at 8.8 mil, 9 liters, you've got no problem. You get very short delivery times. And again, we're not seeing any audible difference between between the pipes. So the key takeaways, cool down effect of pipe is significant and can lead to extended delivery times and long runs. The traditional pipe sizes would lead to extended delivery times and will not be compliant with CP1 2020. We would recommend taking a manifold approach with reduced pipe sizes. You don't get noticeable issues with delivering the required flow rates on smaller sizes, even for long lengths. And there really is a minimal difference in audible noise across the pipe sizes. And theoretical time to clear pipe is well represented by testing. One other thing we want to note is off the back of this, when we went through the testing originally, the pipe work that we tested didn't actually have system RAS approval, which you need to have. We then engaged with manufacturers off the back of that test and got a really good response from market. We've got 2 manufacturers who come through who now have system RAS approval for smaller diameter pipe work. We've got Uponor, 16 mil, 14 mil, and 12 mil. Obviously, those are the external diameters, so that also goes down to the 8.8 mil that we were showing before. And Main Core has 16 mil and 12 mil, and we expect others to follow shortly. So it's really positive to see that response from the market. So questions? I think you can handle this one, Andrew. The question from Dave Lancaster. Do you have any published analysis on the effects of limescale accumulation on the system performance, especially relating to energy efficiency? I think you covered that, yeah?
Not specifically on the system performance, no, not at my fingertips. I'm 100% sure there has been in the past. So it's more about replacement is the and lifetime is the research that I've seen. But in terms of the efficiency of a plate heat exchanger when it's covered in Limescale, I don't have that data at my fingertips, I'm afraid. I don't know if you know of anything, Gareth.
No, I don't. I have to confess.
but I'm sure it's out there, and I might actually, you've intrigued me, so I might do a bit of research, and I think we're going to share some answers after the session, so I might follow that up.
Next question. Actually, I'll follow on. I'll jump one. Question from Samantha Jones. Don't you need to set your HRU temperature much higher than 50 degrees to achieve 50 degrees at the tap? I'll let you give your answer, but this is, I think, something we see often. We saw quite a big design consultancy the other day was coming back and saying you need to set 55 degrees to hit 50 from your HRU to hit 50 degrees at your tap. I think there are two parts to that. One, it isn't actually a requirement to get 50 degrees at your tap, but I think under ENHBC they are looking to that. But Andrew, you've done figures on this.
I was going to refer back to your graphs that you were just showing, Gareth, in that actually, I think probably right anecdotally, and I've seen it on site, is that you do need to set things, and that's generally due to poor install, and that's what we're trying to move away from as an industry. Poor design in terms of layout and long pipe runs and oversized pipe runs, and poor installations in terms of getting the right amount of insulation on or not, and getting that pipe run routed in the right place as per the design. And actually, if Gareth's graph showed quite clearly that once you've got that warm up out of the way, you are easily achieving 50 degrees plus or minus 1 or 2 degrees, which is well within the tolerance of what we actually deal with in the real world on site. So any of our measuring equipment is going to be within that tolerance. So actually, we can achieve that.
And actually on that, we do analysis, we've done analysis on this, and it is a fraction of a degree. If you think of the actual heat loss from a pipe versus you might be delivering 10, 15, 20 kilowatts of flow, what you find is that somewhere between 0.1, 0.2 of a degree you'll get loss by the time you get stability between the 2 points. We don't have instrumentation which will actually measure that, and in practice what you see is we'll be setting to 50 degrees and it'll be very, very close. You won't actually be able to tell the difference. Next question, why not get 55 degrees from the heat pump on the system, increase your COP, then you only require 45 degree domestic hot water set point?
So at some level I would love to do that, but I think as an industry, I think we're more comfortable at 50 degrees because that is well above the band that we know that Legionella propagates. That's not the right word. Excuse me, as I'm not I'm a mechanical engineer, not a public health engineer. I've not always got the right words at my fingertips. But 50 degrees is at the in the range where Legionella is killed, whereas 45 isn't. So although the view of HSE is that an HRU in a typical application is a low volume system, and therefore it doesn't require you to check your temperature at any particular temperature. We just feel that 50 degrees is the right position in terms of giving maximum functionality and maximum safety.
I've got Marko Kosic in my ear at the moment. I can hear him say, in reality, there is nothing stopping you from setting 45 degrees. I think as an industry, we've coalesced around 50 degrees. If you do your Legionella assessments, you can go through and do that. And there are examples elsewhere in the world. I've been shared data from Denmark from a scheme where they did drop to 45 degrees and then monitored Legionella consistently, and they saw no problems with that. But I think from a safety perspective, the balance was felt to be between scalding and Legionella risk that 50 degrees was the right point to set it. I'm conscious on time, so I'm afraid we're going to have to. There was just one last question, which was, what are the practical considerations with respect to manifold domestic hot water systems? I think one point I'd just say is, if you're going to go down that route, minimize the distance between the HRU and the manifold, and then do specify single pipe runs from the manifold to the outlet with no joins on it to minimize risk of leak. And then go as small as you possibly can on the pipes from a resident comfort perspective. Andrew, thank you very much for coming on today. Much appreciated.
Thanks very much for having me. I'm looking forward to the rest of the session.
Thanks a lot.